Self-driving cars are here. Fully autonomous systems like Waymo are being piloted in less complex circumstances. Human-in-the-loop systems like Tesla Autopilot navigate drivers when it is safe to do so, and they let humans take control in ambiguous circumstances. Computers are great at memorization, but not yet great at reasoning. We cannot enumerate to a computer every single circumstance that a car might find itself in. The computer needs to perceive its surroundings, plan how to take actions, execute control over the situation, and respond to changing circumstances inside and outside of the car. Lex Fridman has worked on autonomous vehicles with companies like Google and Tesla. He recently taught a class on deep learning for semi-autonomous vehicles at MIT, which is freely available online on YouTube. I recommend checking out those videos. They are awesome and really informative and actually not too technically dense. It's pretty interesting. Well, there are technically dense parts of it, but parts of it are just entertaining. There was so much ground to cover in this conversation because I have simply not talked in detail to many people who are involved in self-driving cars. Most of the conversation was higher level. How do you even approach this problem? What is the hardware and software architecture of a car? Lex had really satisfactory answers for these. They were not necessarily conclusive, but they were interesting. I really enjoyed talking to Lex, and if you want to hear more from him, check out his podcast. It's called Take It Uneasy, which is about jiu-jitsu. It's about judo and wrestling and learning and self-discipline. Totally unrelated to software engineering, but you might find it interesting, especially if you like this episode. Spring is a season of growth and change. Have you been thinking you'd be happier at a new job? If you're dreaming about a new job and have been waiting for the right time to make a move, go to hired.com/sedaily today. Hired makes finding work enjoyable. Hired uses an algorithmic job matching tool in combination with a talent advocate who will walk you through the process of finding a better job. Maybe you want more flexible hours, or more money, or remote work. Maybe you want to work at Zillow, or Squarespace, or Postmates, or some of the other top technology companies that are desperately looking for engineers on Hired. You and your skills are in high demand. You listen to a software engineering podcast in your spare time, so you're clearly passionate about technology. Check out hired.com/sedaily to get a special offer for Software Engineering Daily listeners. A $600 signing bonus from Hired when you find that great job that gives you the respect and the salary that you deserve as a talented engineer. I love Hired because it puts you in charge. Go to hired.com/sedaily, and thanks to Hired for being a continued long-running sponsor of Software Engineering Daily.
Is Zencastr doing the my side recording too?
Yes. So Zencastr records a client side. It will throw it in your browser cache and it'll upload it at the end. Actually, it streams it to Dropbox and it'll upload a WAV file at the end. And then you can send me your client side recording also at the end, so I can, just in case there's any corruption that occurs in the Zencastr recording, I'll have a backup.
Nice. Does that ever happen?
It does happen sometimes. Very rarely. I would say like 5% of cases, maybe. I guess that's significant, actually.
That is. Yeah, actually, I'm asking because I used to do a lot of interviews for a different kind of thing, athletes.
Really?
Olympic athletes and so on.
Really?
I still have a podcast, I guess, but I haven't talked to
Dude, that's cool.
So I know, but I prefer sort of the in-person because I can look some of these badasses in the eye and it's a little more sort of... And the kind of questions I usually talked about is more about life and like fear and overcoming difficult times. So you kind of want to be in person for some of those.
Listen, hey, it helps to look somebody in the eye and ask them about reinforcement learning too.
That's true. Agreed.
Wait, what's the name of your Olympic athlete podcast?
It's called Not sure I want to advertise it, but it's take it uneasy.
Take
Like
it.
take it easy, but take it uneasy.
I love the name. That's great. Can I put that in the show notes? In fact, can I put this like little preamble conversation in the show? This is good. I like it.
Yeah, absolutely.
Okay, cool. All right. Well, I've got a lot of questions to ask you about deep learning and self-driving if you're ready to get into it.
Yeah, let's do it.
Okay, so Lex Fridman is a postdoc at MIT. He works on self-driving deep learning for semi-autonomous vehicles. Lex, welcome to Software Engineering Daily.
It's good to be here. Thanks, Jeff.
You taught a class in deep learning for semi-autonomous vehicles, and early on in that class, you asked the question, I think this question recurs throughout your class, is driving closer to chess or to everyday conversation when you're looking at it from the point of view of can we automate this? Why is that an important question to ask?
So it's a fascinating question. It's a subset of all kinds of questions that I can summarize as what is intelligence. So it's trying to understand as human beings and as engineers that are trying to build intelligent machines, we have to figure out what tasks require intelligence and what is meant by quote unquote intelligence in that case. So something like everyday conversation or walking, there's a whole category of things that as human beings, we sometimes don't realize how difficult they are when you actually have to sit down and implement that task. So walking and everyday conversation is an example of it. So if I told you to create a chatbot, maybe as a software engineer, you would sit down. Well, that's pretty easy. Maybe you would start. So I'm not a chatbot person, but it's a good example with the Turing test and so on. It's a good example of something that requires intelligence that we take for granted. So if you wanted to implement a chatbot, you might say you build a giant database of different kinds of responses based on the keywords that the other person says. Or you can start to try to understand the syntactical and semantic structure of the sentences. But the moment as you start to encode all of that information, you realize that the database grows, the knowledge base has to grow exponentially, and you have no way of growing that automatically. So it's an example of something when you start to actually build an engineer a system that does this task, you realize how incredibly difficult it is. So that's what we think of like everyday conversation is an example of that. Now driving, it's an open question whether driving is in that category of things that are actually exceptionally difficult and require human level intelligence, or it's something that could be reduced to a problem of detecting obstacles, detecting lanes, staying in the lane, and not hitting obstacles. So it's an open question that we have to face. We're actually building autonomous vehicles that are supposed to drive. There's several trillion miles are driven every year on roads. And there is only, it's tragic, but the number of fatalities in the United States is 38,000 last year. So that means about one fatality per 100-something million miles. Mm-hmm. And that's the kind of error rate you have to achieve with these systems. So you have to ask, well, how to achieve that error rate, to achieve that kind of low margin of error, what problem needs to be solved? Is it as simple as just detecting obstacles and avoiding them? Or is it something where we have to create a system that has an understanding of the physics of the world, an understanding of the human intent when you're looking at pedestrians and so on? There's just these millions of factors that you have to consider. Can they be reduced to something simple?
These components of autonomous driving that you outline in the class are perception, localization, mapping, control, planning, driver state. So when you're breaking self-driving into these different components, is that taking an opinion that self-driving falls in one of the camps of being closer to chess or closer to everyday conversation, or is it sort of a hedge between those?
Yeah, so that's a great question. I think it's not really, it is, so breaking it down into those modules means you're leaning towards saying it's closer to chess. So that's a step towards, so by chess, I mean something that's...
It's well-defined.
It's well defined. You can formalize it. There's piece. There's concept of pieces. There's concepts of moves, actions. There's concepts of what the world encompasses, and the breaking autonomous vehicles into these modules of perception, control. Really, it's those two: perception and control. Is going towards the camp of chess.
Which is a problem that we're much more comfortable approaching as computer scientists, at least with our contemporary techniques.
Yes, that's really well put. So with the contemporary techniques, if you think of software engineering, it's exactly the task of formalizing formalizing the problem, formalizing the solution. I mean, you have to really draw out the entire thing on paper. There's no ability for systems to say, okay, well, 90% of the task we don't really know how to solve, but the system will figure it out as it goes along. You can't write a program like that in the sort of in the current approaches. A program that goes out there and has a human life at stake.
Okay, so I want to talk about some of the technical aspects here. So deep learning is useful for a variety of problems in self-driving cars. What are some of those problems where you can apply deep learning?
So deep learning is a type of machine learning. Given how successful deep learning has been, really, it can be just as comfortably referred to as machine learning. Is most of the problems where it's been effective has been dominated by deep learning, and so deep learning has become machine learning. So machine learning is a set of techniques where you learn from data. A system is able to know nothing or very little in the beginning, and given a lot of data and human annotation of that data. Human annotation meaning a human being steps in and says what is going on in this data that's useful for solving the task. So given the human annotation and the data, you're able to learn how to behave in this world, or to learn to predict things about the data, to extract knowledge from the data. And so that's machine learning, that's deep learning. And in the driving domain, a passenger car, has four wheels. It's tasked with, it can accelerate, decelerate. It can, at the sort of go left, go right, or more specifically, it can turn its steering wheel. It can steer. And really, those are the only actions. You can speed up, slow down, and you can steer. And so, and then there's an external world going on around the car. So it's tasked with perceiving that external world to the degree that it needs to understand enough to be able to accelerate, decelerate, and steer. Okay, so you don't have to do any learning there. You can do, the perception can be using a sensor like LiDAR and map the external environment and save that map, build a giant map of the external, three-dimensional map of the external world, and localize yourself based on that map by using this LiDAR sensor that gives you depth information about around you. That's a non-learning approach. Learning says, well, I'll encode some information at the beginning, but I'm going to learn about the way the world changes, I'm going to learn about the way the world moves. I'm going to learn how the world looks visually in different situations. So what is a lane marking? I'm going to learn what a lane marking is by looking at hundreds of thousands of lane markings, having a human being step in and help me label the times when there's a lane marking, label the part of the image that's the lane marking. And over time, I'm able to generalize over videos I've never seen before of what a lane marking is. Mm-hmm. A Tesla vehicle, for example, is one that used to use up until the end of last year a Mobileye-based system, and now they have their own, a deep learning-based system, where it's predicting lane markings. And there's 100,000 plus cars on the road today that are driving themselves autonomously. Tesla vehicles are able to drive for hundreds of miles on the highway and stay in the lane. So it's able to it's doing exactly that with a single camera detecting lane. And that's done with machine learning.
Bugsnag is an error monitoring tool that enables developers to identify, prioritize, and replicate bugs in a time-efficient and enjoyable manner. Automatically capture errors and diagnostic data in any app. See errors grouped by root cause and focus on fixing errors that have the greatest user impact. Instantly track the performance of each application release with interactive dashboards. Automatically capture a stack trace for every error and get automatic breadcrumbs for crashes so that you can easily reproduce and fix any error. To date, Bugsnag has processed over 10 billion application crashes from thousands of top technology companies. To get started, go to bugsnag.com/sedaily and create an account. It takes 3 minutes to get up and running, and Airbnb, Lyft, and Shopify are already using Bugsnag for their bug tracking and crash monitoring. Try all the features for free at bugsnag.com/sedaily. Thanks to Bugsnag for being a sponsor of Software Engineering Daily. It's much appreciated. So we did a show recently about deep learning and reinforcement learning as applied to VizDoom. That you might have heard of that. It's like basically, you play Doom, or you're a bot playing Doom, and they use reinforcement learning and deep learning. And it's a comparable problem to driving around because you're like navigating a dungeon, you're evading foes or engaging with foes in certain interaction patterns. And that show was an introduction for me to how deep learning and reinforcement learning are both key to this class of problems. So as you write, neural networks are great at memorization and not yet great at reasoning. But reinforcement learning is brute force propagation of outcomes to knowledge about states and actions. Explain what the shortcomings of raw deep learning are and how reinforcement learning can shore this up with some reasoning.
Sure. So to be clear, so you mentioned raw deep learning. I think sort of the precise way to describe that is called supervised learning. It's most of the success in deep learning has come from this category of techniques called supervised learning, where every single piece of data that's fed into the learning system has been touched in some way by a human being to say what's going on in this particular piece of data. So for images with lane markings, it's marking the lanes in the image. For ImageNet competitions, that's marking cat versus dog. Marking for an image, is this a cat, is this a dog, or is this some other kind of animal? That's supervised learning, and most of the successes have come from that, up to date. But in terms of application, in terms of value. Now, that's what I refer to as memorization. So you're memorizing at a very low grade level. You're memorizing what another human being has annotated for you. You're memorizing patterns. Now, what reinforcement learning hopes to provide, and deep reinforcement learning more specifically, is to remove as much as possible the human being from the loop of teaching a system things. So the goal is to generalize over just a few examples provided by a human being in the form of a reward function or a form of an encoded model of a world that provides either perhaps a simulation. So most of the success in reinforcement learning, like the Doom game, is simulation. There's not really another agent walking around in the real world. So simulation. And the idea is the system learns by playing through the different ways that the world can unroll. It acts in different ways and see what those actions have impact on the external world, and seeing how can it act in the future in such a way that maximizes reward. Now, the problem is currently all the reinforcement learning approaches that we know of, and this is true for machine learning in general, have to play for a very long time. We have to play with a very large amount of data in order to learn anything. So if you think as human beings, when we're children or young or still, the learning what a hot stove is like is very quick learning process. So it doesn't require more than maybe 2-3 times to touch a hot stove before you realize, when it's glowing red, or certain visual characteristics or tactile characteristics, or the different sensor inputs are associated with a lot of pain. And that's learned really quickly. Our current best reinforcement learning approaches and deep learning approaches have to touch that stove hundreds of thousands of times before they learn not to touch it. And so the problem there is we're very inefficient learners. So yes, in simulation, you can simulate the touching of a stove over and over to understand which aspects of it lead to punishment, to negative rewards. But if we want to put systems in the real world, like in the driving case, and to teach those systems to avoid crashes, for example, you can't quite, it's not feasible to put that system out there and crash hundreds of thousands of times, tens of thousands of times, in order to learn how to avoid the crashes. So for now, there's this chase towards, well, can we simulate the real world to a sufficiently high resolution that we're able to teach a system of simulation that's actually able to successfully act in the real world. And that's currently an open problem that hasn't been solved.
Right. So you're articulating a specific case of explore versus exploit. We can't really, like I talked to some people at Stripe, this payments company, and they will consciously let payments through that they know are fraudulent, or they will sort of, turn down the dial on their sensitivity to preventing fraud in order to better gather data about fraud. And in that case, okay, we lose some money, not a big deal. You can't do that with self-driving. You can't just let accidents occur and then learn from them. It's too sensitive.
Right. This is one of the biggest challenges for me. The reason I am fascinated by autonomous vehicles, it's one of the first, and I believe it will be the first and the biggest way in which robots really enter our lives, everyday lives. And when you begin to trust, when you have to deal with the issues of trust, of understanding what a role of a robot is in society, from the philosophical level, on the ethics side, to the technological level, to everything. Because the reality is, if we were to design an autonomous vehicle that successfully operates in this world, it's going to have to crash. So in the same way that the credit card fraud will occur, a car will have to be able to, we're going to have to be more forgiving of a car causing a fatality. It's a very dark and difficult, at the philosophical level actually, to allow a machine decision, to put a human being is in the hands of the machine, and the machine acts in such a way that takes that human being's life. That's really difficult for us as a society to understand, because especially in driving, it's such a personal experience. It's usually one human driver, and there's a car, it's a machine. And here's the moment when you give control to that car, and the car acts in such a way that it kills the person. Mm-hmm. But that's very PR-wise, so New York Times coverage and our general sort of view of this is we're not very forgiving. The fatality in a Tesla that happened during Autopilot, it was a big deal. Now,
well, I was just thinking about that. I thought the response was pretty forgiving, though. I mean, you have a car that had the autopilot on, the driver falls asleep, slams into a tractor trailer, decapitating him, and I don't know. I felt like the public didn't really have an outcry, right? You didn't see people with posters in front of Tesla.
So, yes, absolutely. So I agree with you, but the general feel I get from the public, I've talked to a lot of people, especially in the media, and there's a hunger to attack the robots. Like, in general, we see the robots as a Terminator.
Yeah.
At any moment, they'll take over. So there's kind of a desire. There's a desire to find the weak link in the story. And a single fatality, I guess the point I'm trying to make is, in the situation of the Tesla fatality, it was the car didn't actually do anything outside that looks bad, in terms of the car didn't make a decision that's very poor. that it makes perfect sense even for a human being not to see the white truck. It makes sense. What I'm more referring to is if we start allowing machine learning to be part of controlling a vehicle, there's going to be times when a lane marking is completely not seen by a car and it runs off the road. It runs off the road in such a way where any human being would have easily kept the car in control. And so it would lead to a fatality that looks terrible. Or for example, sort of the publicized ethical issues, a car might accelerate into a crowd of people, right? For whatever reason, whatever malfunction perhaps on the sensor side, or whatever the prediction is of the intent that it uses in detecting the pedestrians and predicting where the pedestrians go, it might accelerate into that crowd. Now that's a tragedy, right? But if overall it leads to a much safer, much lower, if it significantly decreases that 38,000 fatalities that we have on the roads today, perhaps it's something that we should be more open to. And that's kind of a society we have to struggle with these questions.
Well, and I think like a good preface to how weird the cases are going to be is like when you have some slides in your course notes where you have these cases where you take an image of, let's say, the Empire State Building, and then you add these minor and like you show it to a computer, and the computer's like, okay, Empire State Building, and you add these minor perturbations to the picture, and if a human looks at it, it's still like, okay, it looks like the Empire State Building. Maybe the picture looks a little fuzzy now, but then you show it to a computer, and it's like, that's an ostrich. And so that just shows how different our perception of the world is compared to a machine. And that's why you're going to get these crazy edge cases that seem like, how on earth did the computer not recognize the lanes there? But if you look into the system, it'd be like, oh, well, the model was trained in this way, and it just didn't learn this edge case.
That's right. That's absolutely right. And I guess I'm trying to imagine cases, but just imagine tragic cases which are very possible, where a machine runs over somebody's daughter, right? A young girl is crossing the street, and a car accelerates. And as a society, we have a really hard time dealing with that concept, because after all, an artificial intelligence system is a technology, and that's heavily regulated when it's on the roads. So that'll come up immediately as a discussion in the public, in public, and the question is, well, should this technology even be part of cars? And that's constantly, this comes up with drones as well, and in other applications of artificial intelligence. So it's definitely on our minds as we're designing machine learning algorithms for the perception side. Exactly as you said, the Empire State Building being mistaken for an ostrich.
Mm-hmm. How does human in the loop? I mean, I wanted to talk about some lower level stuff. Hoping we can get into that eventually. But like hearing you talk about the policy stuff is really interesting, and just the philosophical concerns. So continuing on that high level thread, how does human in the loop fit into the rollout? Do you have a picture for how the ideal rollout strategy is going to work? Because I hear your concerns, and they're very valid, and they're very kind of like hard to deal with. Like, how do you do that? Is human in the loop the gradient that you gradually that gets you off of the humans towards the full autonomy?
Yeah. So I'm a big believer that the human has to remain in the loop as a supervisor and as a teacher of a car. So there's most of the folks building autonomous vehicles, most of my colleagues have come from the success, our robotics folks that have come out of the success of the DARPA challenge, which was a challenge where vehicles were tasked with going through the desert, then going through an urban environment fully autonomously. So no human in the picture. So the car is tasked with dealing with every possible situation and not hitting things and staying in lane and all those kinds of things and not breaking down. So that's the robotics approach. I see that a fully autonomous vehicle that doesn't have a steering wheel and based on a learning system or other optimization-based system is able to fully control itself autonomously, I agree with Warren Buffett. I think he said in 2030, 10% of cars will be fully autonomous in this way. So, and he said that's a hedging. That's a bet. That's a sort of not a conservative bet. That's a risky bet. So I think we're very far away from vehicles being fully autonomous. So before that, I think human will be in the loop, the way Tesla, in the case of Autopilot, is now. So human, whenever the car can't deal with a situation, it has to give control to the human and say, holy crap, help me out here. So the big challenge here, this is the semi-autonomous vehicle approach. The challenge is the moment of holy crap, help me out here shouldn't be 1 or 2 seconds. So the period of the transfer of control currently, like in a Tesla, is sometimes less than a second or a couple of seconds. It depends. The red hands of shame come up, as they're called, in the Tesla, where these red hands glow and you're told to take control of the vehicle. Mm-hmm. That's very few seconds. The ultimate successful system to me, you said, how would this be realized? I think it would be a system that's able to 10 seconds out tell a human being to wake up, to bring their attention back to the road. And one of the missing pieces there, just to quickly say, is our current cars on the road today, for the most part, have no driver-facing cameras or any sensors that are able to detect the driver, except the steering wheel pressure to determine that the hands are on the wheel. So your vehicle, our cars, have no idea about our state at all, whether we're drunk, sober, sleepy, distracted, in the seat at all. That there has no information about us, about us personally, each individual human being, and just general global state of where our eyes are looking, where are directed, where our head is directed. And that information, which I'm a big proponent of, is crucial to make a car that's able to hand over control safely and give plenty of time to do so.
Hosting this podcast is my full-time job, but I love to build software. I'm constantly writing down ideas for products, the user experience designs, the software architecture, and even the pricing models. Of course, someone needs to write the actual code for these products that I think about. For building and scaling my software products, I use TopTal. TopTal is the best place to find reasonably priced, extremely talented software engineers to build your projects from scratch or to scale your workforce. Get started today and receive a free pair of Apple AirPods after your first 20 hours of work by signing up at toptal.com/sedaily. There is none of the frustration of interviewing freelancers who aren't suitable for the job. 90% of TopTal clients hire the first expert that they are introduced to. The average time to getting matched with a top developer is less than 24 hours, so you can get your project started quickly. Go to toptal.com/sedaily to start working with an engineer who can build your project, or who can add to the workforce of the company that you work at. I've used TopTal to build 3 separate engineering projects, and I genuinely love the product. Also, as a special offer to Software Engineering Daily listeners, TopTal will be sending out a pair of Apple AirPods to everyone who signs up through our link and engages in a minimum of 20 work hours. To check it out and start putting your ideas into action, go to toptal.com/sedaily. And if you're an engineer looking for freelance work, I also recommend TopTal. All of the developers I've worked with have been very happy with the platform. Thanks to TopTal for being a sponsor of Software Engineering Daily. So engineers who are listening to this podcast oftentimes they tune in to get a high-level view of how to build certain things. And if you were building a web app, you would learn model view controller or client server With a self-driving car, I don't really understand how the different systems fit together. So we talked about these components, perception, localization, mapping, and so on. Is there some best practices for how these systems are put together today? Can you, I guess, give me an overview for the software architecture of a self-driving car?
So sure, there's no best practices. First of all, that I mean, it's such an open world. We don't. There's so many different approaches in terms of this, from the very subtle, like the thousands of parameters that control every algorithm, to just how the pieces fit together, which sensors are used, and so on. There's just a lot of variety. But in terms of the what is it, the abstract classes of the different approaches, is there's first, you have to have an ability, what's called SLAM, simultaneous localization and mapping. You have to be able to find out where you are in the world. So as a car, you need to be able to position yourself in the three-dimensional world. That can be done in a bunch of ways. One is having already, so first of all, it can be done with having a pretty good map of the world, like Google Maps, and having a GPS. Okay, so that's one very crude estimate of where you're located. A GPS location, latitude, longitude, will tell you where you are in that map, and you can do some basic information: which road I'm on, how close I'm into the intersection, which lane I'm on, and obviously GPS is very noisy. So that's one estimate, and there could be another estimate from, so that, but you build that separate system as a software engineer. You would build that system that says, I'm going to, the input to the function is my GPS coordinates, and I have a database that's a Google Maps, and it puts me to those GPS coordinates and says, okay, I'm in the left lane on this road, and I am 100 meters away from this intersection. That's one little module. Another module will be, okay, I'll have a stereo vision camera, which means there's two cameras positioned close to each other, looking out into the external world, and that camera is able to locate the different objects in the environment, and estimate crudely their depth, meaning the three-dimensional position, the point cloud of where they're located. So the pedestrian, traffic lights, signs, and so on. And that's another little function that says the input is two images coming at 30 plus frames a second, and the output says I am located at this position relative to the traffic sign, the pedestrian, the other objects in the scene. So triangulating everything together. All right, so now I have two pieces if I have implement both these functions, I have two pieces of information that says my GPS coordinates and my approximate triangulation of where I'm located relative to those objects. And I can fuse those together. It's decision fusion or sensor fusion, data fusion, where you take those two pieces of information and combine them to make a slightly better estimate about where you're located in that world. The whole point is to be able to locate yourself as accurately as possible in the semantic structure of what this task is. So in driving task, you have to be in the lane. You have to not be hitting things, other obstacles in the scene, and you have to be navigating, moving around to get to some location. So in that sense, that's part one, is you localize yourself based on, it's plug and play. Another developer might come up and say, I have a LiDAR, and that LiDAR will be able to do a much better job than your stupid stereo vision camera to localize, to give you a better position in this world. But we can all just combine those functions together with sensor fusion and chase the more and more and more accurate localization. And the second part of driving is, once you know where you are, you want to, and when the other objects are, you want to move around those objects. So that's where the control planning happens. And the way you do it is, you have a three-dimensional model of the world with some degree of uncertainty, and you generate thousands of different trajectories for yourself and the trajectories for others that you believe based on your model how other objects move, other vehicles, other pedestrians. And based on all those trajectories, it's an optimization problem for the optimization-based approach to pick which is the best trajectory. For the learning best approach, you use something like reinforcement learning to say what is the best trajectory around those objects. And that's it. That's driving. Perceive the world and then move in that world.
When you're teaching the course in self-driving deep learning, what have been the concepts that are most difficult for the students to grasp?
It's a good question.
Or maybe you could, if that's a tough question, like talk about how you sequence the course in self-driving deep learning, or talk about how, if somebody's listening to this and they want to know how to get started. I mean, obviously there's courses, I think there's a Coursera course, but maybe you have some abstract suggestions for how to strategize about the learning process.
Right. So I think it's just a really good question to say what the students struggle with most, and just to answer it quickly.
Sure. Yeah.
Is I think as not just students but PhD students and research scientists, professors, everybody is struggling with the question of why something works. So from the very basic neural feed forward, fully connected neural networks to all the different flavors of neural networks, convolutional neural networks, recurrent neural networks for deep reinforcement learning, figuring out why something works so that when something doesn't work, you know how to fix it. So why there's a bunch of parameters that control the behavior of a neural network. And so what do I set each individual parameter to make it work for my particular application? So at gaining an intuition, this is the process of learning, I think, in the case of a deep learning course, like the one I taught, like the others out there, is gaining an intuition about what works and what doesn't. So how many nodes in a network, how many layers, what kind of optimization algorithms, what kind of learning parameters, learning rate, what kind of pre-processing on the data is needed. Well, what kind of so there's a lot of different parameters that control, especially with reinforcement learning, that control the training process. And so we start, the way I usually teach and the way I learn myself is really boil down every single type of approach to the simplest possible problem. So look at a very small neural network and learn how, for example, if looking at backpropagation, which is the process of training a network that is producing random results, how do you take that network and over time train it to produce the correct results? That's the process of backpropagation. Backpropagating errors through the network such that they adjust its weights not to make those errors. So you can start with a network of 100 million parameters, or you can start with a network with just 10 parameters. And to visualize and play around and see how the different hyperparameters of training a network affect the way the weights are adjusted. Just look at toy problems for each one to slowly gain an intuition. Because the problem is when you scale the size of a network, that's where the magic happens, sort of quote unquote, but we don't have a good intuition about why it happens. And so why, in the case of deep reinforcement learning, a system that knows nothing is able to learn over time how to play an Atari game is a mystery. It's one of the it would seem through this kind of brute force process of reward and punishment, ability to learn abstract notions of what it takes to win a game would seem to be impossible, but it works. And so it's over time you start to gain an intuition of why it might work. That's the challenge.
You know what's funny about this is I used to be a poker player back in the day, and back when it was kind of easier to win money playing poker online. But one of the things, the people who were successful were the people who read these books about mathematics and poker math, or they could articulate. Many of them could articulate mathematically why a play was good, why a strategy was useful. And, we always used to mock the people who were, instinctive players and like, I've got a feel for this thing. Some of the players who would play by feel, they would be successful. But over time, the people who were mathematically oriented just dominated them. They always had this, a reason for why they did something. But it's just funny that like now you're talking about a branch of computer science where basically we don't really know how to talk about this formally. And I've heard multiple people say this, like, you have to develop this intuitive feel for what's going to work in deep learning. Like, why is that? How did we get here?
Well, it's interesting because, in the case of poker, you're probably the math guys and girls they succeeded because they're able to silence the irrational parts of our brain that says, like, I have a feeling that the flush is coming or something. Like, you're able to look at the actual odds and calculate statistically what is the right move here, and based on that information, start to play with the bluffing and all that kind of stuff. But in the case, so it's hard because that's the scientific way to give that up, to say, to always explore how intelligence can emerge requires some intuition. So you have to let go of the need to prove stuff. So I come from the theoretical computer science background, where you have to prove, P versus NP. You have to prove the complexity of the running time complexity of an algorithm. And the idea that you have no way to prove, but it just works, was viewed very negatively in academia when I started. I think that's changed completely with the success of deep learning. And it's actually the reason why deep learning is just another word for neural networks. It's the reason why neural networks have gone through a couple of winters, AI winters, that because we don't understand why they work, but they seem to work, it captivates the minds of people and they get super excited. They start thinking that they will solve everything in the world. We have created general intelligence. That was true when the first perceptron came out in the 50s, I think. It makes, they're going to solve everything. They're going to fly to the moon. They're going to, flying cars for sure will be around. But the reality is, no, these are just effective tools, and we're slowly trying to discover, in the same way that Darwin sailed around the world discovering what the hell is the mechanism behind the evolution, the diversity that we see in the world. That's how we're trying to sail around the neural network world and try to understand what is the mechanism behind the emergent ability of these networks to predict stuff. Cat versus dog at the simplest level, but at the coolest and most difficult level is the reinforcement, or even unsupervised learning, how you're able to find generalized patterns from nothing, essentially, from no dictionary, no supervised learning, human input.
Okay, so I could talk to you for a long time about this, but we're kind of running up against time. Drawing to the close of the interview, and I wanted to ask you some about the business of self-driving and how these companies are strategizing about it, how they're thinking about it. I read that you're interested in jiu-jitsu, or you practice jiu-jitsu, and I think of the strategy of Google as very jiu-jitsu-y in the self-driving world, because it seems like they're very much like trying to lay as low as possible. And then I don't know. How do you see the different players in the self-driving space, and how do you contrast their strategies? Do you have any predictions about how they're going to roll out things?
Oh, it's interesting. So I used to work at Google, and I now work a lot with Teslas. And it's a very different approach of Elon Musk and Google, or Waymo now. As one is, yes, Google is Waymo. The approach is to stay low. It's to stay quiet, design vehicles that are very safe, never hit anything. They map at a very high resolution the world around them, and travel at 35 miles an hour, at 40 miles an hour around a very well mapped safe street. The Elon Musk approach is to say basically everybody in the auto industry is scared, and I'm going to, just like you go to Mars, I'm going to release fully autonomous vehicles by next year, and say we're going to do it. We're going to, shoot to the moon and get it done. And that's his approach, and not shy away, and on Twitter promise things, and literally, like I said, 100,000 plus vehicles are driving themselves autonomously on the roads today. This is sort of the little known secret of Tesla, is autopilot, for those that haven't driven it, is really pretty advanced in terms of automation capability. So those are the two approaches. I'm generally a fan, in terms of just personally speaking, I'm a fan of the bold and the brave and the risk takers in the world. And I believe that in order to reduce from 38,000 fatalities to 0 fatalities, we have to take risks. We have to be brave. We have to be willing to lose our entire company on an idea. And that's exactly what you have to do with the autonomous vehicles. Because if your car kills several hundred people from a malfunction, there's a very big risk you're taking in PR, or the government stepping in and shutting down the company and so on. So I'm a big fan of Tesla in that way. But I'm also, because we're working closely with NHTSA, which is a government organization tasked with ensuring that vehicles on the road are safe, I also am well aware of safety and how important that is. So, there's a lot of my colleagues in computer science sometimes are so enamored by the coolness of a technology that they don't think about the safety implications. This is sort of the worry that people have about creating artificial intelligence, that us nerds will create this awesome AI and forget to make it ethically sound, to make sure it makes safe decisions, ethically sound decisions. But all that said, I really despise caution, because and sort of being careful. Because I think the whole idea of science and innovation is being brave and bold in these ideas. That said, Google, I think, so that's one side. That's just me personally, sort of on a horse with a sword. But in terms of business side, what is the right bet here? I think Google has been exceptionally successful at playing the long game. And I think Google has a lot more to lose than Tesla. So I think, as I said, autonomous vehicles will not be here until, I'm with Warren Buffett. He's rarely wrong. So I think they won't be here for a couple of decades. So as a business decision, it's not a good one to go all in on autonomous vehicles at this time. Even though the public is generally very hopeful and optimistic about, there's been a lot of companies that promise, in 2020, in 2022, in 2025, we'll have fully autonomous vehicles. Toyota, Ford, everybody and their grandmother has promised that they'll have fully autonomous vehicles. But when the reality, my bet is that the realities will be a little farther out, because of all the technology side, the policy side, the societal side, just all of those are huge challenges to overcome. But to overcome them, I believe we need the risk takers. So I'm a huge supporter of our friend Elon.
Yes. Okay, so last question to wrap up. Deep learning and machine learning, these fields are so rich. There's so much going on in them. There's this chart you have in one of your presentations that I really like that shows basically, the trajectory of a person who is learning about deep learning, and it's like you start off like, oh, this is so intimidating. Then very quickly you're like, oh, I know everything and this is going to be awesome. And then it drops off again. And you're like, you realize you know nothing about the field because it's so deep and there's so much going on. Do you feel like we're witnessing a field that's going to bifurcate away from computer science because it is so deep?
So when you say bifurcate,
so like in the same way that there didn't used to be computer science, that didn't used to be a thing. So it's like, we went from like kind of the engineering and math departments, and then we got this specialty of computer science. It almost feels like machine learning or deep learning might be a new field.
That's a really interesting idea. That's really, really interesting. I haven't actually heard that articulated in that way before. That's the feeling I actually have. The experience I have is there's a lot of folks, there's so much interest. There's young students coming to me every day saying, I'm fascinated by deep learning, right? They're not talking about I'm fascinated by databases or JavaScript frameworks or like the software engineering concept or theoretical computer science, big O, or system architecture. So it almost feels like there's this very hot topic that's actually counter to the way computer science is taught.
Right.
So it's a fascinating idea that you would have like a deep learning engineer that's completely
Because you don't need to know databases. You don't need to know model view controller. You don't need to know big O. Like, you don't really need any of this stuff.
Of course. Yeah, well, absolutely.
It helps.
Really
it doesn't hurt.
Yeah, well, so you need to know all that stuff if you want to innovate the future of deep learning architectures. But you're right. There's a lot of companies out there that sort of need to solve practical problems with machine learning, and for that's essentially that's kind of called like data science now. It's when you basically are cleaning data sets, organizing data sets, and extracting information from them using various methods, statistical or machine learning. But really, that could be its own discipline. That's a really fascinating thing to think about. But I hope not, because I hope computers. It's a weird thing to think about, because computer science is infiltrating everything. It's mechanical engineering, electrical engineering, aerospace, every single field, library sciences, like psychology. So psychologists now all have to code. It's the people in psychology who aren't able to program are finding themselves left behind, because most, with the advent of Mechanical Turk, you want to be able to use computers to put together cool experiments. And so it's hard to know what computer science will be in 30 years, because software engineering is becoming the core of every discipline. And so it's a really interesting question to think about, what that evolves, where robotics fits into this whole picture too. So yeah, that's a great question. I think we're going to be doing deep learning. Like if you're a literature major in college, I think in 20 years you'll probably be using TensorFlow for your homework.
All right. Well, Lex, it's been really fun talking to you. The time flew by.
Yeah. Thanks, Jeff. Thanks
Okay,
so
cool.
much.
Vivid Cortex is the best way to improve your database performance, efficiency, and uptime. It's a cloud-hosted monitoring platform that eliminates your most critical visibility gap, providing insights at 1-second granularity into production database workload and query performance. It measures the execution and resource consumption of every statement and transaction, so you can proactively fix future database issues before they impact customers. To learn more, visit vividcortex.com/sedaily and find out why companies like GitHub, DigitalOcean, and Yelp all use Vivid Cortex to see deeper into their database performance. Learn more at vividcortex.com/sedaily and get started today with Vivid Cortex.
Wow!